Okay, so remember last time we were dealing with just truth tables and different kinds of logical statements and logical connectives. Remember, whenever we write P or Q, we're talking about a proposition, okay? And these propositions, all it means is it's like a sentence that can be either true or false, yes? And it's clear to us whether it's true or false. Now, there will be something else we'll talk about. It's like called a predicate proposition, where there will be a variable, okay, where then we sort of have a question as to whether it's true or false until we know what the variable value is. We already kind of saw that in one of our examples. I oftentimes like to refer to that as an open sentence, whereas I think of a proposition as being a sentence that has either a true or false value. Something that has a variable in it, I often will call that an open sentence, because it's like, I don't know until you tell me what the value is, right? I mean, there was one that said like, x plus 2y is equal to 10 or something, right? Technically speaking, we could think of that as a sentence, but I can't evaluate its truthfulness or falsehood until you tell me what x and y are explicitly, okay? That would be an open sentence. Just by way of review, before we kind of jump in here, let's make a little truth table here. So, okay, so here's P, here's Q, here's P or Q, here's P and Q, okay, here's P. Okay, what does this mean if I put the circle plus? That's exclusive or Q. P implies Q, okay, so that's if P then Q. And then P if and only if Q, okay? And I mean, there are other things that we could write here. For instance, we could use the negation symbol. All the negation is going to do is turn a true into a false and vice versa, yes? Okay, what are the different combinations we could have? Well, I usually like to just write true, true, false, false, true, false, true, false. P or Q, and again, we thought about these even intuitively. We said, hey, I have an intuitive feel for when an or statement is actually true, or whether someone has violated that statement and aren't being truthful, yeah? So P or Q is true, so long as one of them is true, or both, yeah? Okay, so this is gonna go true, 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 false, okay? On the other hand, P and Q, there I'm making a verbal promise that both things are true, yes? So all of these are going to be false, save for the first one here, right? False, false, false. Okay, P circle plus Q, well, that's the one that sounds a little bit more like the English language. Usually when you say or, you oftentimes really mean like an exclusive or, yes? It's like one or the other, but not both. So the only difference between the exclusive or and the normal disjunctive or, remember I'm using some like technical language here. Disjunction was the regular or, conjunction was the regular and. We have this exclusive or. What's that going to be? Only difference is the first one is false, and then it's true, true, false, just like it was for the or case. If P then Q, this is very important. It's probably the most important logical statement in all of mathematics. If P then Q, if the premise, which is the if part, is false, we're off the hook, and the entire if-then statement is automatically true, yes? So if I said something like, if you get an A on the final, then I'll give you an A in the class. You don't get an A on the final, there's no way that you could accuse me of being a liar. Does that make sense? The statement is vacuously true in that case, right? So in both the cases where the premise, the P part, the if part is false, the whole conditional statement is true, okay? And of course, if you get an A on the final and I give you an A in the class, then I have been true to my word, yeah? I did it, I gave you an A, yeah? The only time you would consider me to have been a liar is if you did indeed get an A on the final, but then I failed to give you an A in the class, yes? And that's the situation where P is true and Q is false. So that'd be false. And then we talked about the biconditional, right? Remember, so this guy right here is called the conditional, okay? And this right here is called the biconditional, right? The biconditional. And really, this thing is equivalent to saying P implies Q and Q implies P, right? Both of those things are going on. But we said in order for that to be true, they basically P and Q have to have the exact same truth values. Yes, that's what has to be going on. That's why you say, like, if so P if and only if Q, this is like, this means these things are logically equivalent to each other. And so this is true, and then it's false, false, and then true. Okay? Okay, so that's just kind of a review of where we've been, so that we can kind of work our way forward here. Now, let me just say something here. Let me put another couple of things in here. Watch this. What about, well, I don't know. Let me see. I'll put not P here and not Q. Okay, not P, that's fairly easy. So not P, I just have to negate all of the trues and falses, yes? So this would be like false, false, true, true. And of course, this would be false, true, false, true, right? Those would be the varying truth values. Now watch this, I want to show you something. Not P or Q, okay? What if I did not P or Q? Okay, help me out here. Not P or Q, let's stare at this together. Not P, okay, false or Q, false or true, what's that? Right, because I'm using the Q column, yes? False or true is true. Okay, false or false? False. True or true? Well, true. And true or, okay, true. Now, do you notice something? Look at the columns that we've done so far. Do you notice something about the thing I just did and something that I did before? You notice anything? Look, this guy right here is the same as the conditional. What? Right? So they have the exact same truth values no matter what P and Q happen to be. See what I'm saying? When that happens, we actually say that these things, and we'll talk about this in more detail later, we say that these guys right here, these two guys are logically equivalent. And they're logically equivalent to each other. And we could actually write that this is, remember, we don't write equals, we write this weird triple equal sign. That thing is equivalent to P implies Q. Why? Okay, I just want to have kind of a thought-provoking conversation here. Why does it make sense that P implies Q would be logically the same as not P or Q? What do you guys think? Anybody have any insight into that? And my suggestion is that you think about specific examples to help you think that through. Why would those be the same? Yeah.
Because, like you said, the conditional statement, if P is not true, then the whole statement is true. And since you're saying that not P or Q, they're kind of like the same thing as far as like.
Right. So you're thinking about it. So what you're doing is you're thinking about it at a pure sort of analytical level, like just thinking about the different truth values. Yes, that's absolutely right. What I'm wanting is more intuition, like specific situations. Yeah.
Well, it's like if I go to the store, then I'll buy groceries. Then it's like if I don't go to the store, then the other option is, you know, go to the store, don't go to the store or buy groceries. It's so hard to think about. So it's like if I go to the store, then I buy groceries.
If I go to the store, then I'll buy groceries.
I don't go to the store or buy groceries. Because you can choose either.
Yeah. That's right. Yeah, that's a good way to think about it. It's a little bit tricky. There are some ways that we talk about this that might lend itself more. If you use my example even, it's a little bit tricky. But like, if you get an A in the class, or sorry, if you get an A on the final, then you get an A in the class. Apparently, that's logically equivalent to me saying what? Either, or I might say, you don't get an A on the final, or what? Or you get an A in the class. In some sense, I'm kind of communicating to you, unless I'm just a real snake, you know what I'm saying? In some sense, I'm communicating to you, hey, just so you know, if you get an A on that final, you're going to get an A in class. Do you know what I'm saying? I say, hey, don't get an A on the final, or you'll get an A in the class. Then, if you think about that carefully, unless I'm a real snake, I'm sort of making an implicit promise that if you get an A on the final, then I'm going to give you an A in the class. Also, I thought about this as a parent because I say these sorts of things all the time. I say things like, man, this is sort of tricky to say, but like, you don't, eat your vegetables or you don't get dessert. Okay? So what I'm saying is, don't get dessert. I mean, I could flip those things around. It doesn't really matter, right? You don't get dessert or you ate your vegetables, right? So what am I basically communicating to my child? If what? If they eat their vegetables, they're going to get dessert. Does that make sense? Otherwise, my kids would think I was a real snake. You know what I'm saying? So I say, you eat your vegetables or you're not going to get dessert. What I'm saying is, you eat your vegetables, you actually will get dessert. Okay, so that's the sort of thing that's going on here. They are sort of even intuitively, logically equivalent. Do you see what I'm saying? I mean, go over to Chuck's and kind of think about various examples, but it's definitely true. Okay. All right. Any questions on that? Any questions? Let's see here. Share my screen, and we'll go over. I'll share. Yeah. Okay. I think I was somewhere like right here. Yeah. You guys see that all right? Okay. Just did this. Okay, we did our truth table. Again, the conditional is the most important logical statement in mathematics. In fact, I would say it's the most important logical statement, period. It's built, so obviously I said everything is built on the back of ands and ors. Yeah? So it's not surprising that the conditional is equivalent to something that involves an or. You see what I'm saying? Yeah? That it has to go back to one of those basic building block elements, and it does. And again, don't forget the P part is often referred to as the hypothesis or the premise, and the Q part is often referred to as the conclusion. And we made some truth tables about this. Okay? So I don't know if I'm going to go through, maybe we'll do this exercise maybe on Wednesday or something. But here are some examples. Okay, if I'm elected, then I will lower taxes. Okay? When would you consider me to have lied?
I assume you're lying right now.
Yes. Right. So, right. So like if I got elected and then like didn't lower taxes, that makes sense? That's the only time you consider me to be a liar. Now, if I got defeated in the election, which would violate the premise, does that make sense? If I got defeated in the election and then failed to lower taxes, you wouldn't really hold me responsible for that, would you? Right? Hopefully not. Okay. If you get 100%, okay, wait, we've already done that example like ad nauseum. Do you know what I'm saying? Except that I just changed it to 100% on the final. There's something called the Wason selection task. There's an interesting article that I've linked here. It kind of comes from what I would say to be as a flawed worldview. Of course, it's in the realm of evolutionary psychology. It basically deals with how do we even, like, all of us just have this basic instinct in terms of when someone has lied to us, right? Like, we all sort of understand intuitively what's happening with this if-then stuff, even though you've never learned it before. Nobody taught you that. Like, all we did was we came here and we just sort of agreed, oh yeah, that is how things work, right? And this article right here tries to explain that from like an evolutionary psychology perspective, talking about how like hominids at some point stood up and started, stumbling around. And then they started having to, trying to trade with each other. And then eventually they were like, oh man, I need to like know when someone is trying to swindle me. And then logic kind of birthed out of that. But to me, that's just nonsense. Because even if that were true, that doesn't make the logic work. Does that make sense? The logic is something else. It's like outside of that system. All they're doing is kind of observing something that was already true. Do you understand what I'm saying? So where does that emanate from? And I say it emanates from God himself, right? And that's like the argument that C.S. Lewis makes in Miracles. And there's this really good passage on page 32 where he kind of summarizes, at least in the copy that I have that I've listed right there, where he actually summarizes, look, logic and reason is not something that could possibly be explained on an evolutionary paradigm. It just can't. It has to emanate from something outside of that system. You can't have it emanate from something inside. It has to come from the outside. Okay? And I think it's one of his most powerful arguments for the existence of God. It's like, I'm telling you, if you read the first 100 pages of Miracles and you aren't a Christian, by the end of that, I don't know what else to say. I mean, it just kind of lays it out there. To me, it's bulletproof. I can't find any flaws just in his reasoning. And it's essentially what Lewis gives there is the argument that really convinced him of the truth of Christianity. He was a staunch atheist for most of his life, actually. So if P, then Q. So there are lots of other ways that we could, tweak things, and I want to go through some of those. There are other ways we could say it, okay? If P, then Q. We could say P implies Q. We could say Q when P, right? So whenever P happens, Q happens, yes. Q follows from P. P is sufficient for Q. That means when P happens, that is sufficient for Q to happen. Q is necessary for P. Okay, that means that, if P happens, Q necessarily happens. Does that make sense? It's kind of awkward language. P only if Q. So by the way, P if and only if Q is like the biconditional. Another way to say that is P is necessary and sufficient for Q, right? So it's kind of look, I actually put this thing here. The only if one is the tricky one. And so I gave you this extra little pointer down here. It says, sometimes it's helpful to say P only if, in addition, Q. Does that make sense? Think of like P happens. P is not just going to happen by itself. Does that make sense? P happens, if P implies Q is true, P happens only if, in addition, Q happens kind of resistlessly once you have P. Does that make sense? That's why you say P only if Q. The Q and P are, like if you have P, then necessarily it's partnered proposition Q has to follow. Okay? Sort of tricky language that you might see this P implies Q thing stated. Okay? All different ways to say the same thing. Any questions on that? I don't know if I want to spend a ton of time on this. Look, if you go read, I know that like in like Theology 1 and 2, you guys go through Bible Doctrine by Wayne Grudem. There's like a thicker version of that book called Systematic Theology. And I think in both those books, for sure in Systematic Theology, maybe in Bible Doctrine, yes. Yeah, I think, there is a section on this as well. It goes through the doctrine of the Word of God, and it points out these 4 elements that characterize the Word of God. The SCA, scan is the kind of the way I remember it. Sufficiency, clarity, authority, and necessity. Okay, so there's those words sufficiency and necessity coming up in a theological context as well. Basically means the same thing, but this time we're talking about the Word of God as it pertains to, knowledge about salvation. Okay. So the word of God is both necessary and sufficient for knowledge about salvation. Okay? Like someone couldn't just be like born in the jungle and out of their mind completely understand the redemptive plan of God's salvation in the gospel. Does that make sense? I mean, they might have bits and pieces, and they might understand some things about God, but that wouldn't be enough. Okay, so it talks about the sufficiency and the necessity of the word of God as it pertains to, right living and salvation itself. What's amazing to me is God immediately in the book of Genesis starts giving logical commands. He says, if you, right, you can eat of any tree in the garden. If you eat of that tree, what will happen? Then you'll die. Yes? So immediately he makes a conditional statement. This is the covenant I'm making with you. You can live freely and eat of anything that you want. But if you eat of that tree, then you will die. Yes? And he didn't have to say, look, this is how logic works, guys. Here's a truth table. Here's the P's, here's the Q's. No, it was just sort of imprinted on their hearts and minds, and because they bear the image of God, who is the one who, from which logic actually emanates. Okay? There's an interesting passage that I would encourage you to go read in 1 Samuel 23 that has to do with conditionals. Oh, and by the way, if you go read Leviticus, this is kind of funny. Look, if you're a mathematician, Leviticus should be your favorite book, even though everybody else hates it, right? Because it's just a massive collection of logical statements all over the place. It's like, if this, or this, or this, or this, or this, then this and this and this, right? And it's like you just have some really beautiful logic there. And then it will actually come back and clarify things, and it'll give you a logically equivalent statement about cloven, footed animals and whatnot, right? That's all over the place. If you just go read Leviticus 11, you'll see that right there in front of you. 1 Samuel 23 is an interesting story where David and his mighty men are kind of running from Saul, and they go to the men of Keilah, who the Philistines had come and were really threatening. And David and his mighty men kick some tail. Okay, they go down there and they drive out the Philistines. The men of Keilah, the people of Keilah, are extremely grateful. But then Saul catches wind of the fact that they're in Keilah, and David has all his spies everywhere, and he basically is told, "Hey, look, Saul's coming down here with an army, and he knows that you're trapped inside the city walls of Keilah, and he's going to kill you." And so David says, "Bring me the ephod," which is this priestly garment to put on or whatever. He puts the ephod on, and he prays to God, and he said, "Will Saul come down here and try to kill us?" And God says, "Yes." And then David says, "Will the men of Keilah give me up? Like, will they actually betray me even though I just helped them?" And God says, "Yes, they will." And then the passage ends by David saying, "Okay, we're out of here." And then they leave. So God said something that never happened. Do you understand what I'm saying here? He's saying, yes, they will give you up to Saul and you will die. And then David leaves, and that particular thing never happened. Did God lie? Well, his answer was conditional. It was conditioned on those premises being satisfied. Does that make sense? If this does happen, then this, right? So it's helpful there to kind of think about. I've actually had people say, "Hey, God didn't tell the truth on this part." I thought, oh, wait a minute. That's a conditional statement. And the premise was false. But what God did is he gave an answer in the context of if the premise would have been true, then this would have been the outcome. Does that make sense? I don't want to spend a ton of time on that, but it's just interesting to think through. Any questions on that? Okay. All right, here are some other terms that I think it's good for you to be familiar with. P implies Q. If P, then Q, right? So that's kind of the baseline statement. If you flip it around, Q implies P, that's called the converse, okay? Which is pretty cool because, back in the day, that was a pretty popular brand of tennis shoe, okay? So Q implies P is the converse of P implies Q. It's not the same statement, right? I mean, for sure. Let's kind of go here. Let me go in here. Let's see. I want to share this thing. Okay. Sorry. I just want to make sure you understand that these are not the same thing. Okay, so look at this. You guys see that? Okay, let's look at Q implies P, right? So use statements, you can actually tell through truth tables whether they're logically equivalent. You can also think about it, just through intuition. But Q implies P. Okay, let's look at it. True implies true, right? This time we're going in this direction, right? True implies true is true. False implies true. True. Okay, we're already different. You see what I'm saying? The second instance right here for P implies Q is false, and this one's true. What about true implies false? False. And false implies false is true, right? So notice that this is not the same thing as P implies Q. That is very important. You'd be surprised how often actually people try to do that. They try to flip that thing around. Okay. There were other ones. Okay, let me see here. There are other ones like not P implies not Q. Okay, that's called the inverse of P implies Q. Okay. That also is not the same thing. Okay, that is not the same thing. Here, I want to write on here. Okay, so let's see. You guys see this? So this is not the same thing as, not P implies not Q. And I would sort of challenge you to go look at the truth table values. Very different. Okay, and even if you say some examples out loud, they are definitely not the same thing. Not Q implies not P. That's called the contrapositive of P implies Q. Contrapositive. Now, what do you think about that? Let's think about an example. If you get an A on the final, then you get an A in the class. What would not Q implies not P? Okay, so that's P implies Q. What would not Q implies not P be saying?
You won't get an A in the class if you don't get an A on the final.
If you don't get an A in the class, then you didn't get an A on the final, yes? Do you see that that's saying the same thing? It's logically equivalent, yes? Okay, so if I say to you, look, I'm just telling you right now, this is my solemn oath to you. If you don't get an A in the class, then I guarantee you didn't get an A on the final. You see, that's kind of the same thing as me saying, if you get an A on the final, then what? You get an A in the class. I'm telling you, if you go look at the truth tables, they will be exactly the same. So the contrapositive is a very important variation of P implies Q. In fact, when we go to prove stuff, we oftentimes will work with the contrapositive because it will be easier to work with. Okay? There's something called a proof by contraposition that uses the contrapositive, which is logically equivalent. Do not forget that this guy is logically equivalent to P implies Q. Okay? That's very important. Okay? Any questions on that? Questions? All right, moving on. Ooh. Okay, hang on. There we go. Yeah, let's actually skip this example. You could go kind of do that on your own. It's interesting. Remember, converse, flipped it around. Inverse, you say not P implies not Q. Contrapositive, not Q implies not P. Yes. Fairly straightforward, but this is just something I would challenge you to go do on your time. Again, these slides are actually on Canvas. Under the slides module, it's one of the modules in Canvas. So this is something I've kind of been saying. Two propositions are equivalent if they always have the same truth table values. Usually, if they are logically equivalent, there's a way we can see intuitively why that is so. For propositions P, capital P and capital Q, we would write capital P triple equals Q. We've been kind of already doing that. Show that an implication is equivalent to its contrapositive. We've already done that intuitively, yes, just by way of an example, but you could also do it using a truth table. And look, this is an example we already did. P implies Q. We showed that it's equivalent to not P or Q, yes? That was the thing we were talking about with dessert and vegetables, yeah? And the intuition kind of comes from that specific example. Precedence of logical operators, okay? So the kind of chief precedent goes to the not operator. Does that make sense? Not has precedence over everything else. And then or, and then implies. So like the conditional, and then the biconditional has the lowest priority. Okay? So you kind of read this statement right here, P or Q implies not R. Okay? Before you do anything else, you would want to think about negating R. Does that make sense? Whatever R is, you would negate that, right? So that kind of has top priority. And then what has priority between the or and the implies? Right, would I do Q implies not R and then take the result and or that with P? No. You would do the or first because of the operator precedence with logic, and then I would do the implies part. So, I mean, essentially, you can kind of put parentheses around that, and you can also technically put parentheses around this as well. Right, you can kind of do those two logical operations separately, and then take the result and do the conditional. Yes? The conditional would be the last thing that you would do. Any questions on that? After a while, it just becomes, you don't even think about it. You're like, oh yeah, okay. But it's kind of like, I mean, we have PEMDAS for like addition, subtraction, multiplication, division, exponentiation, etc., right? So there's got to be an order of operations in terms of kind of the logical operators as well. Okay. So what about this? Okay, you have the flu during the final. Okay, you skip the final, you pass the class. Okay, so what is? So let's just kind of say this out loud. I won't write it, but P implies not R. Okay, so what does that mean? It implies that you didn't pass the class, right? Okay, if you had the flu during final, then you won't pass the class, right? Or what? Or you skip the final and you don't pass the class. Yeah? It's interesting. Okay. Okay, so these are just applications that I wanted to do. There's lots of things we could talk about. I just, you know, there are some computer science applications, system specifications, Boolean searches, logic circuits. If you went and took like something called DLD over in the engineering department, digital logic design, you would spend lots of times on logic circuits. AI diagnosis method, even things like machine learning, all of that depends on this kind of formalized version of logic that we're talking about here, okay? Basically, all of computer science is built on the back of this kind of symbolized version of logic. But I want to focus more on translating English to propositional logic because that tends to be what we do in math and logic puzzles because they're fun. Man, I used to just be obsessed with logic puzzles. I used to sit there. We'd be on like family vacations. I remember one time we were driving. I'm from California. We were driving up the West Coast to go up to Victoria, Canada, and And I mean, I was car sick the entire time because I was working on these, I had this little logic puzzle book that I was working through. And I would be sitting there trying to do stuff and I'd be like, oh man, I'm feeling sick, right? But logic puzzles, I always think about that and it's a good memory for me, even though I was car sick the entire time. Because I was doing logic puzzles, all right? Okay? So translate this into propositional logic, okay? You can access the internet on campus only if, okay, and the reason I'm doing this, I want to see if you were paying attention a few slides back. You can access the internet on campus only if you are a CS major or you are not a freshman. So why don't you, like with someone right next to you, try to come up with like a symbolic logic representation of that, okay? So do that. Talk to your neighbor.
That's where the arrow is.
Oh, okay, okay.
You are not a
If and only if it's a double. Yeah. Yeah, Sophie.
Okay. So somebody help me out here. We have to name some of these phrases, right? Let's see. We have to name some of these phrases. So like, what letter? Oops. What letter do you want to give to that? All right. Okay. Okay. So I guess that would be Q. Okay. And you are not a freshman? Yeah. So this is like not R basically, right? It's the negation of being a freshman, yeah? Okay, so how would you write this as a logical statement then? Yeah, yes, sir. You said P biconditional, but it doesn't say if and only if. It just says only if, right? So what's it going to be? Right, so it's going to be P implies Q. I don't know, I'm just sort of nervous right now, so I'm going to put parentheses around this stuff. P implies Q or what? You can access the internet on campus only if you're a CS major or
Would this be R because you already have the not in there?
yeah, or not R. Okay. So yeah, is this what most people had? What is there something missing? Yes.
You can take away all of the brackets because the or is it takes precedence. So you can just have P implies Q or not R.
Sure. Yeah, you could do that. Yes. Right. Because the logical operators do that. But is there something missing here? Someone back, you were shaking your head.
I mean, don't you have to have the I mean, there has to be something with the not are. It's just like.
Because it's like you're not a freshman, but you want to tie that back to something. What do you want to tie it back to? So the fact that you can access the internet. Yeah. Okay, so how do you do that? So you're thinking that this right here needs to change. The second part needs to change, right? How's it going to change? P implies not R. Okay. Well, or how about this? You could do this. Isn't this one way you could do it? P, okay, so the fact that you have, what is going on here? How come I can't write, for crying out loud? Okay. There, oh, there we go. P implies, okay, so the ability to access the internet implies one of two things. What are the two things that that implies? Q or, okay, I'm putting the parentheses in here just to be extra cautious, but P or not R. And we may or may not need those. Is this more like what people had? So the ability to access the internet implies that one of two things is going on. Either you're a CS major or you're not a freshman. Does that make sense? Or both. Both of those things could be true. You know what I'm saying? You might be a sophomore CS major, for instance, or something. Yes? Okay. Yes. Okay, so that's how we should think about this for sure. Okay. Any questions on that? All right. I think I'm probably going to stop there. Yeah. Yes. So do you see that? I mean, there's one solution right there. I use different letters. Yes. A implies C or not F, but because A was access, C was computer science, F was freshman. You don't have to use P, Q, and R necessarily. Yeah. So I'm going to stop there. Again, you can read the first two sections of chapter 2. Make sure you get that paper done by midnight tonight. That's it.
So,